Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module we will continue the discussion of antenna, define couple of antenna parameters and then consider a practical antenna. Okay. When we talk of an antenna, we usually think of directive antennas, that is you have a transmitter antenna located in some point and then you have a receiver antenna, and when they talk to each other, that is when the transmitter antenna emits radiation and the receiver antenna receives that radiation, you would want, for most practical purposes, if they are kept in the line of sight kind of a system, that antenna must radiate very nearly in the same direction as the receiver antenna. There is no point if the antenna radiates everywhere and then the receiver gets to receive only part of that radiated field. Okay. So, the ability of an antenna to focus its electromagnetic energy in a given direction is quantified by the term called directivity. Okay. And gain is something that is related closely to the directivity and to the efficiency of the antenna. So, to repeat, directivity of an antenna means that it is the ability of an antenna to radiate efficiently in a given direction, to basically put all of its electromagnetic energy as much as possible into a specific direction. And of course, no real antenna can actually radiate only along a single line. Okay, all radiations have to be a little bit of a broadband. So, we differentiate different type of antennas based on how broad their emission pattern would be, and this emission pattern typically consists of a few main lobe, side lobe, back lobe and so on. Okay. So, if the width of the main lobe is as narrow as possible, then we call this antenna as a antenna with a pencil beam characteristic. Otherwise, we call this antenna with a fan beam characteristic, so whose antenna pattern would be quite wide. Okay. And in any case, both fan beams as well as pencil beams have a better directivity than an antenna which radiates uniformly along everywhere in all the angles, right. So, that such a uniform radiator is what is called as an isotropic radiator. So, an isotropic radiator is one, okay, which takes in a total amount of power P or the radiated power P and spreads it out or spews it out equally in all angles or equal amount in all, independent of an angle basically, because it emits energy of the same value around a radius r, uniformly without any theta dependence. And when you talk of directivity of an antenna, you actually compare your antenna beam pattern or antenna power pattern and you find out the direction at which the maximum energy is radiated and divide that amount of energy with the isotropic radiation. That is, the directive gain of an antenna, or sometimes called as the directivity of an antenna, is the magnitude of your time averaged Poynting vector at a given radial distance r from the antenna where it is maximum. So, we have already seen that for an elementary dipole the Poynting vector is proportional to sine square theta, and clearly at theta equal to 90 degrees or theta max of 90 degrees is when there is a maximum amount of Poynting vector, right, time average Poynting vector. So, you take that value, divide by the isotropic radiation density, which is basically P by 4 pi r square. So, this P by 4 pi r square is the is the Poynting time average Poynting vector of an isotropic radiator. An isotropic radiator radiating equal amounts in all angles. Okay, it's like a spherical or a sphere you can think of, and you now look at the maximum direction for a given antenna, find out the Poynting vector there and then take this particular ratio. So, you already know what is the numerator for the case of an elementary or a short dipole, right. For our short dipole, we have already seen that the radiated power is given by eta pi I0 square delta L by lambda whole square divided by 3. This was of course the power that would be seen at the maximum radiated value or at the maximum angle, or since we are actually not looking at the radiated power, hold on a minute. So, let me come back to this one. So, this is a radiated power, but we were looking for the power density S, right. So, the power density at theta max of 90 degrees for the elementary dipole will actually be given by eta k square I0 square delta L square sin square theta divided by 32 pi square r square. Of course, when theta is equal to 90 degrees, sin square theta will be equal to 1. Okay. So this is the maximum radiation or the Pointing vector that you can actually obtain. The value of the maximum time average Pointing vector is this one. Okay. Now the denominator of P by 4 pi r square actually has to be obtained by first considering the radiated power of a given antenna. Okay. So you know what is the antenna whose directivity that you are measuring. So for that antenna you find out what is the total radiated power. Okay. So this can be found out for the elementary dipole by integrating the second expression over the spherical over the sphere of radius r, correct, and you take this amount of power and divide this amount of power by 4 pi r square to obtain the isotropic equivalent isotropic radiation. So what we mean is that you first measure where the power pattern of your antenna is maximum, okay, that would be theta max, and you will have the power time average power density at that point. Okay. Integrate that one over the sphere, you will also find out what is the total radiated power. Now you assume that that power is actually obtained, or that power is actually spread out or given out by a isotropic radiator in equal amounts. Okay. So you first find out S of theta max, magnitude of that one for your antenna, integrate that S of theta max over the entire sphere, and then find out that whatever the radiated power. Now you take the radiated power and think of this power as coming off from a equivalent isotropic radiator. So for that isotropic radiator, the power density will be radiated power divided by 4 pi r square. Now you form the ratio of these two, you will obtain what is the directivity. Okay. And when you do that, the directivity of the short or the elementary dipole, okay, turns out to be very small. In fact, it of course turns out to be greater than 1 because it is not an isotropic radiator, but this will turn out to be 3 by 2. I will leave this as an exercise for you to show this. Okay. So this 3 by 2 when you express in dB will be about 1.76 dB. So this is not terribly high, but this is also not equal to the minimum value. The minimum directivity of 1 will be obtained only for the case of a isotropic radiator. Okay. In kind of a intuitive terms, what we mean here is that let us consider a radius r, okay, and if this is an isotropic radiator, the power radiated in all directions will be equal. So let us say out of this sphere, the total power that is coming out is P rad by 4 pi r square, or rather P rad is the power coming out, and this radiated power divided by 4 pi r square will be the power density. Okay. Now imagine that you actually have an antenna or your own antenna which radiates only in this narrow region, okay, only in this kind of a cone. Okay. Whatever the power that you radiate of this one, or what is the power density there, if you take that ratio to this P rad by 4 pi r square, okay, that would be the directivity. So obviously this black curve is not at all directive because there is no direction specific region where the electromagnetic energy is concentrated, whereas in that red curve, which actually represents your antenna design, radiates in a particular cone of an angle. So there is a high directivity associated with that. Okay. Let us do a simple example. Let us assume that someone is building an earth to moon communication system. So there is an earth moon communication system. The distance between earth to moon is very large. The distance is about 3.9 into 10 to the power 5 kilometers. Okay, that is the distance that you have, and then on earth you actually put up a small laser. Okay. So this is the laser pointer that I have taken, and assume that the laser pointer is sufficiently intense that it actually emits radiation, creating a cone of uniform illumination. Sorry, my pictures are not very nice, but it produces a cone of uniform illumination, and this cone actually has a diameter of about 2.6 kilometer. Okay. So whatever the or on the surface you actually have a nice spherical patch, and this nice spherical patch has a diameter of 2.6 kilometer, or equivalently 1.3 kilometer of radius. Okay. So this is radius and this is the diameter. Okay. And we assume that the power is actually filling up uniformly over this. So that is the power P that is received on the 2.6 kilometer spot. Okay. So instead of giving you theta max, we have actually given you what is this quantity S of r comma theta max, okay, and this quantity is simply given by the power which is filling up this uniform spot size, right, the power that is on the moon, the spot size on the moon, divided by 4 pi. What is the power, what is the radius of this sphere? That is about 1.3 kilometers, right. So it is 1.3 square. Since every unit is expressed in kilometer, I am not converting it into meter. So this is the power density of my antenna, which creates a uniform illumination of spot size whose radius is 1.3 kilometers on the moon. The directivity of the antenna, of course, if you actually think that this power should have come from a isotropic radiator, so let us actually do that one, right. So isotropic radiator would have radiated the same power, but not over this spot size, right. It would have radiated over 4 pi r square, but r is this distance, the distance from earth to moon, correct. So this would be 3.9 into 10 to the power 5 whole square. So this would be the isotropic radiated power density. Now the directivity, of course, is the ratio of this quantity to this quantity. So when you take the ratio, p will cancel, 4 pi will cancel, and what you actually see is approximately 3.6 into 10 to the power 11, or about 115 dB, okay. Again, the idea is that you have an isotropic radiator which would have radiated power everywhere, the same power, okay, over this particular sphere, but my antenna is radiating only over the small cross section of this big sphere, okay, and that is why laser communication is very important for satellite and earth communications, because of this very high directivity that you can actually obtain. Ordinary antennas cannot focus their electromagnetic energies all the way into such small spot sizes unless you create very special type of an antenna, but a laser which is sufficiently powered enough has a highly coherent light beam which will have a very high directivity and therefore very high ability to focus light onto very narrow directions, okay. So that is the advantage of a laser communication system, okay. So we have so far talked about short dipole or an elementary dipole. We have seen that the elementary dipole does not really have a large directivity, okay, and it is also not a completely practical example, because you do not want to fabricate, you know, just a small nail or a small bead, and even then you have to be careful that this delta L has to be much smaller than the wavelength that you are considering, right. So it is not a nice practical antenna. Practical antennas, as you must have seen, will actually will come in various shapes, but one of the most popular antenna is a long wire antenna. So it is just a big piece of cylindrical wire, okay, of sufficiently large length, which of course will allow you to be used, which of course allow you to use as an antenna, okay. We will look at the fields of such a long antenna, or sometimes called as a long wire antenna, or sometimes called as a linear antenna. Linear is not a very nice word, because although the idea is that it is actually a line kind of an antenna, linear has a specific usage in system theory, linearity versus non-linearity. So we will call this as a long wire antenna, okay. And the long wire antenna is kept along the Z axis, so between say 2 points, say Z1 and Z2, okay, and then of course you have your X and Y, okay. So this is your antenna that we have kept. Let me just illustrate the antenna. I have just considered it to be reasonably, you know, thick, but do not be misled. This is actually a line. I have just exaggerated the picture over this, okay. So this is the long wire antenna. So we are still in the wire or a thin wire like distribution or current element like distribution, okay. So this long wire antenna that we have will of course radiate, and we are again interested in the far field observation point, okay. So we are interested in the far field observation point, but now I need to know what is the current distribution on this antenna, okay. The current distribution on the antenna as a function of Z and time, because this is the Z axis over which we have kept the antenna, will be some I0 of Z times, we are again assuming that it will be a cosine or a sinusoidal variation, but it will also have some phase distributions, cos omega t plus phi of Z. Of course, I can go to the phasor notation for this one by eliminating the time dependence, and the phasor will be some I0 of z e power j psi of z. As in the case of a short dipole, unfortunately I do not know what is this phase psi of z, and I also do not know what is this I0 of z. We need to determine what they are from some other considerations, but what is the magnetic vector potential? Well, luckily the magnetic vector potential would still be z directed, okay. So, this would still be z directed, and these constants mu naught by 4 pi can be taken out, and over the integration limits of z1 to z2, which is where the antenna is located. If you are not happy with z1 and z2, you can take z1 to be equal to minus L by 2 and z2 is equal to plus L by 2, so that your antenna is having a length L, which is given by z2 minus z1 anyway, okay. So, you can think of that way, it does not really matter. And then what is the inside retarded potential or the retarded current distribution? That would be I0 of z e power j psi of z, which is the phase which you do not know, and then e power minus j k r, propagation, that is the distance between the source point and the antenna itself, divided by r. Where is r? Again let us go back to this. So, this is your small r vector, which makes an angle of theta with respect to the z axis, and we are considering this particular source here, okay, at some small distance dz at a height of z prime, or we will simply call this as z. We will not use the prime coordinates to show that it is the source coordinates, okay. Source, normally we represented the source with primed coordinates, we will not do that, that is just notational convenience for me. So, at a height of z and over a short length dz, if you find out what is the distance from this current element to the observation point P, that would be the capital R vector, correct, and this vector itself will be given by z hat vector, and you can now see that there is a relationship between r, small r and z, and that relationship is nothing but r is equal to square root of, or rather r is actually the magnitude of r minus r prime vector, which r prime in this case is equal to z into z hat. So, therefore, this can be written as magnitude of r square plus magnitude of r prime square minus 2r into r prime, correct. But I know that magnitude of r square is nothing but small r square, magnitude of r prime square is simply the position vector here. So, what is the position vector? That position vector is simply z square, right. So, this is z square, and r dot r prime is the angle between z axis or the r prime vector and the r vector, which is the cos theta vector. So, this is minus 2 cos theta r z, the magnitudes of r and z also must be included. Thus, the distance r from the source point to the observation point is actually given by square root of r square plus z square minus 2 r z cos theta, okay, which I can now approximate, assuming that we are so far away from the antenna that r is much larger than z, okay. So, if I approximate that one, then I can pull r square out, okay, of this sign. So, r square pulling out will make it r square root of 1 plus z by r whole square, which I will remove because anyway it is a small quantity, minus 2 z by r cos theta, and I will not remove this one because z by r whole square is a second order term which I can remove, but this is not a second order term. So, I will keep this term as it is, but I will use the binomial approximation of square root of 1 plus x as 1 plus x by 2, okay, in writing this as r 1 minus z by r cos theta. So, this is my approximate value of r, and you please keep this in mind. Why should you keep this in mind? Because if I go back to the vector potential and write this vector potential, of course, as a function of r and theta, will be mu by 4 pi, okay. In the integral, this of course will be along the z axis, okay. So, you have the current element, right. So, you have I0 of z e power j psi of z, which you again do not know, but in the denominator you have e power minus j k r. In the denominator you had capital R, which I can write it as r 1 minus z by r cos theta, okay, and in the numerator I will replace this capital R by the small or the expression for r, which is r, and then you have e power plus j k z cos theta this entire thing over dz, appropriate limits of z1 and z2. Okay, this is what you have. Now e power minus jkr doesn't depend on z, right, because it is only dependent on the small r. So I can pull this person or this equation out of the integral. Okay. Similarly, I will neglect this z by r cos theta in the denominator. Okay. You might ask, why am I neglecting this in the denominator but I am not neglecting the same thing in the denominator? Watch closely. You have a kz cos theta. Okay. If I change z, over a very small value, it's okay, z is changing, z cos theta is also small, so that is also changing, but it is actually getting multiplied by this k, right. So k is very large, and if I change z cos theta such that kz cos theta goes from 0 to pi, then we have completely inverted the current distribution. So it is very important to note that you can make this approximation for capital R in the denominator, but don't carry the approximation in the numerator, because there is a exponential change associated with that approximation. So you do not make this small r approximation or the capital R approximation in the numerator, and therefore end up having to retain this e power j kz cos theta in the numerator. So your vector potential A, which will be the z component, will actually become mu naught e power minus jkr, which I can anyway remove it, 4 pi small r. I can remove this small r also from the integral, because r is not dependent on z, so this will also come out of the integral, and then you have inside the integral z1 to z2, or as I said minus L by 2 to plus L by 2, I0 of z e power j psi of z e to the power j kz cos theta dz. Okay. To proceed further, we of course need to know what is this quantity and what is this quantity, and this is an extremely important problem. We have struggled for more than 100 or 125 years, and no one till today has been able to give a correct and valid expression for I0 of z and e power j psi of z, that is the current amplitude and the current phase, amplitude and the phase of the current on a thin linear or a thin long wire antenna is not known, because it is subject to boundary conditions, environment and other factors. So no one has been actually able to solve this problem, and in fact most antennas do not give you what is the current distribution. In fact, they will ask you to calculate the current distribution. Okay, so this is an extremely important problem. Most antennas do not have a current distribution that is well known and can be written down. Okay, so that's the major problem. So most antenna analysis are to an extent assuming a certain current distribution, calculating the fields, doing measurements, and then going back and fitting the current distributions back. Okay, so that's the iterative kind of a procedure that one has to adopt when studying antennas, because the current distribution in terms of amplitude and the phase is not so easy to obtain for the antennas. So what we do instead, we said that this is supposed to be an antenna whose length is some L, correct, L being Z2 minus Z1. What if we imagine that this length L is actually a lambda by 2 antenna? Okay. Now before we consider the antenna, let us assume that we consider an open-ended transmission line, right. So with an open-ended transmission line, what happens? The current distribution will of course start with 0, reach its peak at lambda by 4 and again go to 0 at lambda by 2, right. From the open-ended terminals of the transmission line, you start at 0, reach at lambda by 4 the peak, and then you go to 0 again at lambda by 2. Now if I open these terminals, instead of making them parallel, I slightly open them up, you more or less expect the current distribution to remain the same, and if I open it up completely, you expect the current distribution to remain same. Okay. I mean, this is of course a slight hand waving kind of a thing going on, because there is no reason why this current distribution should be preferred over this current distribution or over this current distribution. While yes, the black line seems to be intuitively correct, but it is not a rigorously known thing that it has to be like that. Okay. In fact, it cannot be like that, because the current is maximum in the middle here, but the voltage will actually be equal to 0. So if you actually connect this one to the power source or the voltage source, it says that there is actually no power transmitted at this particular point because the voltage is 0 and the current is maximum. So, there is essentially no power going into that. So, this distribution is not exactly correct, but it kind of gives you some sort of a approximate and a reasonably closed form expressions for the calculated fields, and that is the reason why we proceed with this approximation. So, we remove all the other possibly correct but unverified and we replace the antenna current distribution to look like this. So, this is our antenna current distribution that we have. Okay. This is again, as I said, an approximation to this. Of course, to the other end you actually connect the current sources. So, this is the approximation for the current. Okay. So, we will assume that this this of course is a cosine function, right. So, if you take this one and take this as z equal to 0 and this as some z equal to L by 2, this as z equal to minus L by 2, then you will have a cosine function with phase phi of z equal to 0 and I0 of z being given by I naught cos kz. Okay. So, this is the maximum value of I naught. Okay. You can then substitute this I naught cos kz into this expression and substitute psi of z into this expression, and you will still realize that this integral is not so simple to solve, but if you do solve, you will actually get the z component to be mu naught e power minus j k r I0 divided by 2 pi k r cos of pi by 2 cos theta divided by sin square theta. So, this is your z component, and you can actually find out what would be the electric field component and the magnetic field component, or if you are not interested in finding the magnetic field component, that is fine. You find out the electric field component, you find out only the theta component of this electric field, okay, and then take the magnitude of this theta component divided by 2 eta, so as to obtain the time average Poynting vector. The magnitude of the time average Poynting vector can be obtained by taking the magnitude of the theta component, which actually turns out to be minus j omega a theta. Okay. So, you already know what is the theta component for Az, or you can express Az in terms of theta and r component. Do not worry about the r because you are not interested in that one, you are only interested in the theta component, which you can then obtain. So, this is actually E theta is minus j omega a theta. You can go back and write that one. The corresponding electric field will be given by j eta I naught by 2 pi r e to the power minus j k r cos of pi by 2 cos theta divided by sin theta along theta direction. This is the electric field phasor. Okay. Of course, if you look at the magnitude of electric field, then all this j term will go away and you square up each term, e power minus j k r magnitude will also be equal to 1, and this fellow will be proportional to cos square of pi by 2 cos theta divided by sin square of theta. Okay. And if you plot the power pattern of this antenna in the polar plot, so this is the polar plot with increasing theta along the positive and negative directions, and this will actually turn out to be something like this. Okay. And if we calculate what is the directivity of this antenna, which is the long wire antenna, this turns out to be about power radiated from this one. The power radiated for typical values turns out to be about 36 times I square, and the directivity of this antenna turns out to be about 2.15 dB. Okay. And this antenna pattern, this is at theta equal to 90, which is again the maximum value where it is occurring. Theta equal to 0, you do not actually have any power out there, and this antenna pattern is much better approximated by the donut than the previous elementary dipole antenna. So, what you have seen is that the analysis of antennas is not so easy, okay, because it involves spherical coordinates and you have to crunch a lot of equations in order to arrive at reasonably accurate answers. Moreover, you need to know the amplitude of the current and the phase of the current distribution over the source, which is also not very easy to know. It is more or less an iterative kind of a scenario that we are looking at, but single antennas usually do not give you large amount of directivities. So, you can actually take multiple such antennas, create what is called as an array in order to obtain larger or increased directivity. Thank you very much.